Hello, good morning. I am Puskar Rai, and I'm here to do video presentation on Hadoop Big Data Management System and their components as a part of assessment of big data analytics. I'm using my personal laptop, and the camera is from the laptop itself. Uh, Before I begin, I want to thank ma'am for this opportunity. So now let's start. Okay. The first slide is about Hadoop Framework overview. The Hadoop Framework is an open source platform that facilitates the distributed storage and processing of large datasets across clusters of computers, making it a vital tool for handling big data. At its core, Hadoop comprises of two main components, which are the Hadoop Distributed File System, also known as HDFS, which provides a reliable and scalable method for storing vast amounts of data. And the other one is MapReduce, a powerful programming model designed for processing that data efficiently. This architecture enables organizations to harness the power of the data by allowing them to store it in a fault tolerant environment and process it parallelly, ultimately leading to a faster insight and more informed decision making. Okay, now let's go to the next slide, which is Hadoop Distributed File System. It is a key component of the Hadoop framework designed to store large volumes of data across multiple machines in a distributed manner. SDFS operates on a master slave architecture where the name node acts as the master server, managing the metadata and the file system namespace, while data nodes, as you can see in the picture, serves as the slave storing the actual data. The system organizes file into blocks and distributes these blocks across various data nodes, which can be located in different rack. As you can see, there are rack 1 and rack 2. This will enhance data redundancy and fault tolerance through replication. Clients interact with HDFS to react and write data, relying on the name node for file information and data nodes for actual data access. This architecture ensures high availability, reliability, and scalability, making SDFS an essential component for handling big data workload. Now we can go to next slide, which is the core component of Hadoop. So there are three core components of Hadoop, which are MapReduce, HDFS, and YAM. They work together to enable the efficient processing and storage of large data sets. First, the HDFS provides a scalable and fault-tolerant storage solution, allowing users to store vast amount of data across multiple machines. HDFS divides files into blocks, which are distributed among data nodes, ensuring data redundancy and high availability through replication. Okay, next part is the next core component is MapReduce. It is the processing engine of Hadoop that facilitates the execution of data processing tasks in a distributed environment. It operates through a two-step process: the map phase, where data is filtered and sorted, and the reduce phase, where the processed data is aggregated and outputted. This model enables efficient parallel processing of large datasets across the cluster. Finally, the other component is YARN, which is yet another resource negotiator. It acts as the resource management layer, handling the scheduling and allocation of resources across various applications running on the Hadoop cluster. Yarn enables multiple data processing frameworks to run concurrently, enhancing the overall efficiency and flexibility of the system. Together, these three components form a robust framework for handling big data challenge, making Hadoop a leading solution in the field of data analytics. All right, so we can go to next slide, which is extended Hadoop ecosystem component. While there I have only shown five, there are more than five. The extended Hadoop ecosystem consists of various components that enhance the functionality and versatility of the core Hadoop framework. Among these, PySpark enables Python developers to leverage the power of Apache Spark for large-scale data processing, offering an intuitive interface for data manipulation and machine learning. HBase serves as a NoSQL database that provides real-time read and write access to large data, making it ideal for applications requiring quick data retrieval. So the next one is Hive. It is a data warehousing solution that allows users to query and manage large datasets using a SQL-like language, simplifying the analysis of big data without requiring extensive programming knowledge. Peak offers a high-level scripting language for processing and analyzing data in Hadoop, facilitating complex data transformation with ease. Additionally, the last one is Uzi serves as a Flowbox scheduler, enabling users to manage and orchestrate complex data processing tasks in a seamless manner. While these components significantly enhance the Hadoop system, like I said, there are many other tools and frameworks available, each contributing to the overall capability of Hadoop in handling diverse data processing and analyzing need. All right, let's go to next slide, which is data flow programming model, also known as FPM. It is a powerful approach to data processing that conceptualizes workflow as interconnected actions, making it particularly suitable for parallel computing in distributed systems like Hadoop. In this model, programmers can visualize processes as directed graphs where the nodes represent individual processing tasks and the edge illustrates the flow of data between these tasks. This graphical representation allows for a clear understanding of how data is transformed and moved through various stages of processing. One key advantage of DFM is its ability to enhance scalability and fault tolerance. By efficiently allocating tasks across multiple nodes in a distributed environment, this model ensures that processing can scale with the size of the data and the number of available resources. Furthermore, DFFPM is designed to maintain smooth operation even in the face of failures. Okay, like I said, DFM structure allows programmers to visualize processes as directed graphs. All right, now next we can go about and explain SQL databases versus no SQL database. Okay, SQL database are structured database while no SQL database are no non-structured database. SQL databases, which are also relational database, are structured and uses a predefined schema to organize data into table with rows and columns. They leverage structured query language SQL for defining and manipulating data. SQL databases are known for the strong consistency, integrity, and the ability to handle complex queries, making them ideal for applications requiring complex transactions such as banking system and enterprises application. They excel in scenarios where data relationships are critical and where the data structure is stable and well defined. On the other hand, as shown in the picture, NoSQL database are designed for flexibility and scalability, often accommodating on structured or semi-structured data. They do not require a fixed schema, unlike SQL, allowing for a rapid change and the ability to store a wide variety of data types such as JSON or XML. NoSQL databases come in various types, including data stores, key value stores, column family stores, and graph databases. They are well suited for big data applications, real time web application, and scenarios where high availability and horizontal scalability are essential. NoSQL database prioritize performance and can handle large volume of data across distributed system, often sacrificing some data of consistency for speed and flexibility. So the next slide is about data warehouse in comparison to data lake. In this slide, I have shown the features of both of these data warehouse and data lake. For the first feature I will be explaining is about data structure. It is structured data, whereas data lake is structured or it could be semi-structured or unstructured data. Schema wise, data warehouse is schema on write, which is data defined before loading. Schema on read data is which data lake is schema on read. Likewise, storage cost for data storage is generally higher, but data lake is usually cheaper. Data processing wise, both are ETL. The other one is use case. Data warehouse are used for data business intelligence and reporting, whereas data lakes are used for big data analytics and data exploration. Lastly, I have put the conclusion slide. So in conclusion, let's talk about Hadoop's influence. I'm reading from the slide. Hadoop serves as a fundamental framework for managing and analyzing vast amount of information. It is used for big data. So other one I included is key components, which includes SDFS, MapReduce, and YARN. I have explained about these in the previous slides. And lastly, I have included the future outlook. And point wise, it is progress in cloud connectivity and data management practices. Uh, The next one is potential integration of machine learning and artificial intelligence futures. And lastly, rising demand for insight and predictive analytics will drive the evolution of Hadoop to prioritize efficiency, usability, and compatibility. Okay, thank you.